Today I want to talk about semiconductors and introduce our new unit. Semiconductors are kind of interesting, but before we get that, just some real basics for those of you who haven't had physics or don't remember your physics too much. Electrical charge is represented with the variable Q, and it's measured in coulombs, which you may remember from chemistry. 1 coulomb is just a large amount of charge. It's 6.25 times 10 to the 18th charges, either the charge on an electron or a charge on a proton, and that is 1 coulomb. Voltage, measured or represented with the variable capital V, is the electrical equivalent of pressure. So, for example, the plugs in this room are 120 volts. It's a measure of the electrical pressure involved. And it's measured in joules per coulomb, but because it's used so frequently, it's given its own unit called the volt. Oddly enough, volt is abbreviated capital V as well, and so the variable for voltage is V, and the unit for voltage is V, which causes unending confusion. Electrical current is represented by the variable I, and it's the electrical equivalent of flow rate. And it turns out current is the amount of charge per unit time. So it's measured in coulombs per second, but again, because it's used so frequently in physics, it's given its own unit called the amp. Finally, resistance R, variable R, is the opposition to the flow of charge, and it's measured in ohms. Now, you should say, oh, ohm should be abbreviated capital O, but because capital O looks too much like a zero, we use the Greek character omega to represent that one. Now, a couple quick notes about electrical current. Ben Franklin, one of our first electricians, believed that it was positive charge that flowed around a circuit. So he defined electrical current as the charge flowing from the positive end of the battery, which had too much positive charge, to the negative end. And so he would write current going this way. And so the red arrow here represents the way that Ben Franklin would draw a current. It wasn't until much later, around the turn of the 1900s, that the electron was discovered, J.J. Thomson and fellows. And we actually discovered, it's the electron that's free to move in a circuit. And the electron, as you can see in the circuit here, represented by the yellow arrows, actually flows from the negative terminal, which has too many negative charges, to the positive terminal, which has a deficit of charge. Now, because too many books have been written already, in every single physics textbook, we tend to use Ben Franklin's definition of current, even though it's wrong. So in all electrical circuits, we always draw a current as flowing from the positive terminal to the negative terminal, even though we know it's actually electrons flowing the other direction. What do we call this kind of current? We call it the conventional current, because it's sort of what we got used to doing. Doesn't change the value, it just changes the direction, but honestly, it doesn't actually change our results all that much. Why do I bring this up? Well, we're about to move into semiconductors, sort of modern electronics. So now we're moving from, I moved from Ben Franklin in the 1780s to the discovery of the electron early last century to now modern electronics, which sort of took the stage around the 1950s. What was going on then? Up to that point, everybody used vacuum tubes. It's hard to even describe what they were in your day and age, but let me quickly explain what's going on here. If you remember on the periodic table, there is a nice little line here that goes along the table right along here, and that line separates the conductors from the non-conductors on most periodic tables. And the elements that border this on both sides are called semiconductors. Over here on this side, you've got the conductors, all the metals. Over here, you've got the non-conductors, noble gases, and the other materials over here. But right along this edge, this material can actually act either as a conductor or non-conductor or an insulator. That makes them useful as switches, which is what all our computers are based on. We usually use silicon in most modern ones, although germanium was used in early electronics. And we still use some of these other elements nearby here as well, like arsenic, phosphorus, aluminum, gallium, you name it. Real quick, you're going to cringe, I know, but you might remember electron configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Well, it's just the last last part here that I'm interested in. Silicon, a single atom, has an electron configuration or loose dot structure of just 4 valence electrons. Now, that in itself, not very happy. Remember, they tend to want the octet. So what happens here? Silicon in a pure crystal will actually bond with four of its neighbors in a little tetrahedral structure, and thereby each of its neighboring ones will share one electron. And I didn't draw all the ones on here, but each of the silicons then end up with, especially the one that's in the middle here, bonded to its four neighbors, has a covalent bond where it's sharing four electrons with its four neighbors, but giving each one a perfect octet. You've got now very happy silicon atoms in this structure, and it turns out pure silicon is a fairly poor insulator. You can make it conduct if you put huge electric fields on it, but basically it's an insulator. How can we make it a little bit more interesting? Well, this is where things get exciting. So here's, and forgive me, I've done a very simple job here. So here's our lattice of silicon atoms. Again, please remember these are tetrahedral structures. That's not planar like I drew here, but you can sort of see the octets for each of these silicon atoms. What can make this a little bit more interesting is simply by adding what are other nearby elements. So take a look at this one real quick. If you replace a couple of the silicon atoms with phosphorus atoms. And if you look back at the periodic table, you'll notice that phosphorus is 1 over on the periodic table, which means each phosphorus atom has 5 valence electrons. So now you got this excess electron in here, and phosphorus is like, whoa, wait a second, I just want my octet. And so what happens? This electron gets passed around the crystal like a hot potato. Nobody wants it, but it's free to move around anywhere it wants inside of the crystal lattice. What do you call a material where you've got free mobile charges? It's a conductor. And so when you have this extra one in there, this whole crystal becomes a conductor because I've got mobile ones. And usually you end up doping it with quite a few phosphorus atoms, not just one. Because it's got extra negative charges in it, we call this an N-type semiconductor. Negative extra electrons, N-type silicon or semiconductors. You can also go the reverse route. If you replace a few of the silicon atoms with boron only has 3 valence electrons. And so what you end up here is a missing electron in this one, and we call this a hole. A hole meaning there should be an electron there, but there's not. And again, this gets passed around the conductor. You're like, how does it get passed around? Well, for example, this boron here may steal the electron from here. Now, this one would have a hole. And it's like, well, this silicon's like, no, I don't want the hole. So it steals an electron from this one. Actually, that's a bad example. This one over here to replace that one. So what happens is this hole actually travels around this crystal as well because nobody wants to have that missing electron. Everybody wants to have their octet. Again, believe it or not, what you've got here is basically like a positive charge, a missing electron moving around this thing. And again, anytime you have a charge, even in this case, the absence of a charge that's free to move around, this becomes a conductor. And this is called a p-type conductor because we've got a positively charged missing spot, a hole in this thing that really wants to have an electron in it. And this is also a conductor. And you're like, great, why do we have this N-type silicon and the p-type silicon? Why do we need 2 different types? Well, things get exciting when you put them together. You're like, wait, what happens? So imagine you had 2 of these crystals in contact with each other. So imagine you put them right against each other. Think about it. The N-type silicon has an extra electron right here, and the p-type silicon is missing an electron right here. What's going to happen? Electrons are naturally going to flow across this way to replace or fill up all the holes. And if you just left these 2 pieces of silicon in contact with each other, yep, the extra electrons here would fill in all the holes they could over here, and then the whole process would stop. But here's where it gets exciting. If you connect this to a battery on both sides, the battery here, this is the negative end of the battery. Electrons are going to be flowing off of this around the circuit this way. And guess what? As it loses electrons here, new electrons will flow in. And you might say, well, wait, why do electrons want to flow in here? Well, remember, this is actually electrically neutral up to this point. The number of protons and electrons were the same. But now I move this electron over here, and now it's actually slightly positively charged. It's actually going to attract electrons into it. And over here, this was electrically neutral, but once this falls in here, we've got an excess electron on this side. Electrons would very happily leave this to go to a place here which is positively charged. What do I have now? I've got a circuit. Electrons can flow from the negative terminal battery through this thing and then leave this side and come back over here. Interestingly enough, will electrons flow the other way? We're like, or could you actually reverse the battery? Say, put the battery this way so that the positive end was this way and the negative end was this way. And the answer is, believe it or not, it would not have a current. Why? If you had this on the negative side here, this side would become negative. The positively charged holes would get attracted to this side, but they wouldn't have any electrons or anything to make them flow into the circuit. And over on this side, which I'd now be positive, the electrons would be attracted over that way. They may leave, but there's nothing now to go across this barrier. Electrons can only flow this direction across this barrier. They cannot go the opposite way. This device was one of the first devices which only allowed current to flow one direction. Now again, remember, because we're using Ben Franklin's conventional current, we would say the current can only flow this direction. Remember, conventional current is drawn the opposite direction electrons flow. It cannot flow the opposite direction in this circuit. And this is our first semiconductor device. Something that using just silicon and doping it with a few other elements, you can create a device where only electrons only flow one way.
Here's a picture of a diode. These are some
Device. Now, diodes come in various shapes and sizes. Here's a really big, powerful one, or power one, but most of them, just most of the time, have a little tiny, look like a little plastic black thing. Inside of it is the silicon wrapped up in plastic, and they'll have a little stripe on one side. The stripe corresponds to the N-type material over on this side. So remember, electrons can go from this side to this side. Which way does current go? Well, current can actually go this way. Remember, again, the way current's defined. And so this symbol, or the schematic symbol, every electronic device has one, looks like this, where this arrow right here represents the direction that current can flow, which is a little bizarre with the line over here. But yeah, current can go this way. And so the line here represents this line right here. So current can flow through this diode, this direction. Which way are electrons flowing? Electrons are flowing the opposite direction. So the electrons are free to go through this thing in this direction, not in the opposite direction. So just kind of remember that when you see these things. You can actually make the electron jumps. So we talked about you can dope in different ways. That when the electron goes from the N-type to the P-type, you can actually make the gap large enough. In other words, the hole deep enough. So when the electron goes from the N to the P, it actually falls into the hole. And you might remember that from chemistry. When electrons went from one subshell to another, when they jump from one to another, they actually emitted photons. Well, if you make the jump large enough, you can emit light. And what kind of diode is that? It's called a light-emitting diode, which is such a mouthful that we usually just call them LEDs. And so in this case, current will flow through these in the direction here. But every LED, since it's a diode, will only allow current to go the one direction. So in this case, current here, here's our positive end, here's our battery. The positive end here will force conventional current around the circuit this way, which is allowed to go through this thing this way. Sorry, fix my eyes here. And this will light up red. But if you hook this up this way and you try to force current through the LED this direction, it will not light. In fact, no current at all will flow through it. And so light-emitting diodes are a practical application of this whole thing. We use a lot of them in this chapter. So what's happening here? So as electrons go from one to the other, the band gap here is what it's called, from one valence shell to another, is large enough that it actually emits red light. The symbol for a light-emitting diode is like a regular diode, except they'll usually have a couple of lines coming out of it up here in the top if you look, and that's the schematic diagram for a light-emitting diode. Looks like a diode, but it's got photons coming out. There's a bunch of different types of diodes. I don't expect you to know all of them. There's a generic diode, one we talked about before. There's something called a Schottky diode, a Shockley diode, a constant current diode, is a Zener diode, a light-emitting diode, that one we've talked about already. A photodiode, which accepts photons to get it going, a step-recovering diode, a tunnel diode, a variactor diode, a pin diode, and the old-fashioned vacuum tube. All of these are valid. The only two you're going to see are generic diodes and light-emitting diodes in this unit. If you want to talk about the other ones, I will later. Here's some actual pictures of diodes. It's crazy. I showed you a couple of them, but typically you'll see these light-emitting diodes usually in plastic cases, photodiodes like that. Here's a vacuum tube. Laser diodes are actually the same thing. Avalanche diodes. Oh my gracious. Gun diodes makes microwaves. Peltier diodes. We've played with some of those. Those are the ones that get hot and cold on one side. Those are also diodes. You can use diodes to actually convert alternating current into direct current. And I'm afraid my animation's not working here. If you connect enough of them. Alternating current is what we have in the wall sockets in this room. It's constantly changing from positive to negative. It goes like this, positive, negative, where this is the positive side and this is a negative. It's a sinusoidal function. But we can use that to convert into DC, which is what, for example, your computer adapters or iPad adapters do. And they'll have 4 diodes in them, which will actually convert it. I don't want to go through the details of this case, but this terminal will become positive, this terminal becomes negative. No matter what you're putting in at these 2 points right here is where your alternating current comes in. Not too big of a deal.
This right here is a
The other thing I want to talk about real quick is you can actually take 3 layers of silicon and make what's called a transistor. And this is the start of our switches. One type is called an NPN transistor because it's got an N-type, P-type, and N-dope silicon all connected here. And there's also a PNP-type transistor, which has it set up this way. To make these conduct, for an NPN transistor, you've got to make the base positive. And if you do that, you get a very large current that flows through this way. In fact, you can use this as an amplifier. For a PNP transistor, you need to make the base negative, and that allows a large current to flow through it this way. Again, both of these are amplifiers. They're switches, but it takes a very small current on the base to produce a very large current between the collector and emitter. So in this case, a NPN transistor, if you make the base positive, it turns it on. Make it negative, it turns it off. For a PNP, negative voltage on the base turns it on, positive turns it off. And you can even turn them partially on and partially off, which is where you can actually make an audio amplifier. If you take a NPN transistor up here and a PNP transistor here and run one of these signals into it, when it goes positive up here, it'll turn on the NPN transistor. This is the base of it up here. And so that'll connect it to positive voltage, which will produce a very large positive voltage here on the output. And then if you change it to, for example, the negative voltage will turn off the NPN transistor, but a negative voltage on the PNP will connect this to the ground and produce this very large negative voltage. And so you can create an amplifier. So if you hook this up, they just throw a little resistor here, but connect this to a speaker instead. You can take a small input from a guitar pickup or a microphone and drive an actual speaker. Yeah, there's a few more parts involved. It turns out you've got to have some bias resistors and capacitors in there. We haven't talked about capacitors yet, or resistors exactly. But yeah, you can make a very simple amplifier. You might say, Ms. Clammer, you're rushing through transistors. Yeah, because I want to get to our next topic, which is the MOSFET. And you're like, Mr. Clammer, MOSFET? Yeah. MOSFET is an acronym for Metal Oxide Semiconductor Field Effect Transistor. And you're like, what? Yeah, MOSFET for short. This is what most and almost all modern electronics use. So your cell phones, your iPads, your computers, just about everything uses these, not regular transistors anymore. Why? These are crazy useful. How do you make this? You just start with two N-type pieces of doped silicon along with some P-type over here. And the P-type here doesn't have much to it. In this case, we renamed them. We still have a gate which controls it, and then we have source and drain instead of collector and emitter. The silicon oxide layer is glass. It's an insulator. So you've got this connected here, the drain connected here. And what's interesting on this one is the metal, the gate here is connected to a piece of metal on top here, but the metal is actually insulated away from the P-type by some glass. And you're like, whoa, whoa, what's going on here? Well, this is sort of like a transistor, but something interesting happens here. If you apply a positive voltage to the gate, you charge that metal positively, it attracts electrons towards that gate. Well, you've got excess electrons here now, and even in P-type silicon, you still have some electrons that are mobile. You can attract electrons up here, and now this becomes basically N-type silicon as well. And remember, N-type silicon is a conductor, and now you've got N-type silicon in contact with N-type silicon in contact with N-type silicon. What can happen here? You can now suddenly have a large current flow from one to the other. So now you can get a current that will flow through this between the source and the drain. And this is where things get interesting. With a very, very tiny applied voltage here, you can turn this thing on and off. And this is where it gets fun. And so this is the schematic for an N-type silicon or N-type MOSFET. And even a small positive voltage, turning it on or off, a small positive voltage here can run large motors and devices that are connected to much larger voltages here. So the positive voltage here, positive 5 in this case, to the gate turns on this and can run a large positive or large motor running on 12 volts DC. Because it doesn't take much to do it, because that glass layer is very, very thin, MOSFETs are static sensitive. What do I mean by that? If you apply a larger voltage to this than it's designed for, say for example I applied 100 volts on here, that 100 volts would actually break through this glass layer here between the gate and this and actually form a conducting layer, at which point the N-channel MOSFET is toast. Which is why, for example, all memory chips are made out of MOSFETs. All CPUs are made of MOSFETs, which is why you always ground yourself before you actually replace memory chips or CPUs inside of your computer, or if you're sticking in a GPU card. They're all very, very sensitive because of the very thin glass layer that's between the gate and the rest of the gate, or between the gate and the rest of the device. There's two types of MOSFETs, just like there's two types of transistors. The N-channel is a lot like an NPN transistor, where you put a positive voltage here to turn it on, a positive voltage at the gate to turn it on. And there's a P-channel, where the parts below it here are P. Sorry, if you remember, these are both N down here. P-channel has P on both sides of this. And to turn this on, you need to actually make the gate negative to attract protons, or holes, basically. And the same thing here with a PNP transistor, you apply negative voltage here or current to make this turn on. Most of the time we're going to be working with these, but you can work with both of them in digital circuits, both P-type and N-type. All right, there's lots of ways to draw MOSFETs and schematics. The ones we're going to be using are these. They're called enhancement mode MOSFETs. So you'll see this diagram a lot, but you might see some of the other ones if I'm lazy. There's some real quick applications of MOSFETs. USB thumb drives are made with just specially constructed MOSFETs In this case, they've got a layer of glass in the normal gate, which is called a floating gate, and then they have another control gate up here that's connected to a wire. Thumb drives store on and off conditions, true and false conditions, even when they're not connected to power. How do they do that? Well, in this case, if they create a large enough positive voltage on the control gate, like a very, very large positive voltage, you can actually force some of this positive charge through this insulator to what's called the floating gate. And because the floating gate's surrounded by glass on both sides, once you force these in, and by the way, for those who are purists, yeah, technically what I'm doing here is pulling electrons out of this area to the positive part here, but leaving a positive charge behind. Even when you disconnect this floating gate has positive charge on it, which means this whole thing attracts electrons down here, which means this thing is on, or is a conductor, which means we say that it stores a 1 bit, a true bit. If it's off, if I remove all this negative charge down here, or positive charge here by forcing electrons in, if I'm making this very, very negative, you can turn this gate off. And off means when it's not conducting, which we say in logic terms is a 0. This is Boolean logic. In Boolean logic, you either work with 1s or 0s, trues or falses. But yeah, this one stores that charge permanently. One quick note on this one, though. Each time you write or erase one of these bits in one of your thumb drives, you actually somewhat destroy this layer right here each time you do that. And so thumb drives, you're actually limited to about 10,000 read-writes or 10,000 write cycles before you permanently damage the insulator to the point that it can't be used. If you've got an SSD drive in your computer, or you're using your iPad, every time you read or write from it, you destroy that insulator a bit. That's how your iPad stores information when you've got it powered off. They have spares, which is why your iPad's constantly checking this. Whenever it decides, oh, wait a second, I wrote a 1, but I'm reading a 0, or I wrote a 0 and I'm reading a 1, it actually swaps out the bad memory cell and uses some other spare ones that it has. All right, yeah, here's a picture of a thumb drive, just to give you a feel for it. All right, now we get into digital logic, which is what your homework involves tonight. Digital logic, the absence of voltage, 0 is considered a false. The presence of a voltage, either 3.3 or 5 volts, a 1 is considered to be a true. Again, the whole Boolean logic. You can create logic gates using simple MOSFET circuits. The circuit shown over here to the side is a NOT gate. And you're like, whoa, 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 what's going on here? A NOT gate, if you put in a positive, you get out a negative. And you're like, wait, what's going on here? Well, this is an N-type one down here, so that positive input turns this on. And so this symbol here stands for ground, or 0 volts. It connects the output to 0 volts. Switches this one on, and so you get 0 volts out here and output. Actually, I should have done this better, but forgive me for a second. You get 0 out if you put in like 3.3 volts over here. This is a P-type up here. The positive does not turn it on. Alternately, if you put in a negative voltage, I have to quick erase here real quick. If I put in 0 volts, what happens? A whole different thing goes on here. If you put in 0 volts, that's a negative charge. The negative turns off the N-type down here, but turns on this one, which connects this through. And so now suddenly I've got 5 volts on the output. And so this is called a NOT gate. Whatever you put in, you get the opposite. So in this case, 0 volts would represent false. What's not false? True, which is represented by the 5 volts. In these, we actually talk about what are called truth tables. So this is the symbol for a NOT gate. This is the electronics for a NOT gate. If you put in 0 on the input, this is considered A. The output over here is not A. It's 1. So if you put in 1, you get a 0 or you get a 1 output. And a not is represented by a line over the top of that. It means not A. And so the output here is not A. So if you put in a 0, you get a 1. If you put in a 1 into the input of a NOT gate, you get out a 0. And again, 0 and 1s are represented by the absence or presence of a voltage. We talked about that before. There are other logic gates as well. An AND gate, and you're like, whoa, 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 what's an AND gate? An AND gate has two inputs, an A and a B. And the output of this, and it's a little bizarre, is represented by a dot. So an AND gate is represented by that. So when is an AND gate true? The output of an AND gate only is true if both A input and B input are true. Then this is true. The output becomes true. So if you put in a logical 1, a voltage on both of these, you'll get out a 1 on the output here. But anything else, if you put in a 0 for A and a 0 for B, the absence of voltage on both of those, the output's 0. If you just put in a voltage for B but not A, output's 0. Or a voltage just for A but not B, the output is 0. So the only way you can get a logical 1 output or a voltage out of an AND gate is if you put in 1s on both of those. And I could show you the circuit for these, but it's not worth it. And the symbol for an OR gate or an AND gate looks like this. There's also an OR gate. Its symbol looks like this, kind of triangular. An OR gate is a logical OR. The output of that is true if A is true, if B is true, or if B and A is true. So in this case, notice if you make B true, even if A is false, the output's true. Or if A is true, B is false, the output's still true. Or if both of them are true, inputs are true, you get the output. And so here's input A, here's input B. And this is the only really annoying thing. In Boolean algebra, an OR is represented by a plus sign. And I always think, wait a second, plus sign should represent an AND gate, like AND, you adding things together. But no, in Boolean logic, it's represented by that. An OR gate, if A is true or B is true, or both of them are true, the output becomes true. So if you put in a 1 here and a voltage there and not a voltage there, you would still get a voltage out here. There are also some other kinds of logic gates I just want to quick show you. You don't need to memorize these. There's a NAND gate, a NOR gate, and an XOR gate. Now, before you panic too much, basically a NAND gate is an AND gate, like that, followed by a NOT gate. But because that's too much work, they simply draw it just with an AND gate with a little O on the end here to represent the NOT gate. A NAND gate is just like an AND gate, but exactly the opposite output. We invert the output. So normally an AND gate only gave you a true output if both inputs were true. In this case now it only gives you a false if both inputs are true. XOR gate is just like an OR gate followed by an inverter or a NOT gate. And so its output is exactly opposite that of an OR gate. With an OR gate before, if A was true or B was true, you would get an output of 1. Now, the only time you get an output of 1 is when you have both inputs are 0. And so this is not A or B. Exclusive OR is a little bit more interesting, and this is one circuit we've never talked about before. Sorry, for all the inputs here, A and B are over here. XOR, exclusive OR, is what XOR stands for. And exclusive OR is only the output is true if A is true or B is true, but not if both of them are true. So it has to be exclusively one or the other, but not both of them. And the symbol for exclusive OR is kind of bizarre. It's an OR with a circle around it. So the plus sign for an OR, but with the circle around it. And that's an exclusive OR. And believe it or not, using these circuits, you can actually make digital logic, like a complete computer. In fact, the original NASA computer that flew to the moon was made entirely out of NAND gates. Just lots and lots of NAND gates, and actually they had a few NOR gates in it too. Actually, wait, let me take that back. It may have been entirely out of NOR gates. I got to look that up again. So, in your homework tonight, you're going to be doing a couple of things. And I've missed one of them is figuring out NOR gates and OR gates. But take a look at this one real quick. Please construct a circuit for the following Boolean expressions. You want to do A, and if you remember that symbol there is AND, not B. So how do you do that? Well, you start out with an AND gate, and you want A to go into it, and you want not B to be added to it. How do you do that? We're going to take and use a NOT gate, and so now this produces A, this is input A, and not B. So A and not B. And I'll do one more with you real quick. A and B or B. How do you do that one? Here's input A. Here's input B. And what am I going to do here? I'm going to put them into an AND gate. Remember, this is the symbol for an AND gate. And then I wanted to not only do that first, but then I want to take the output of that and OR it with B again. Here's the symbol for an OR gate. And how do I do that? I'm going to connect B, a little circle here, and actually put it also into this gate, the other OR gate. And so the output of this is A and B. And then I or do it with B again. And so I know it's a little bit overwhelming. You're like, whoa, Ms. Clymer, I can't follow it. Just think about it. The output of this will be A and B or B. Because this is an OR gate and I'm ORing it with B. I'm doing that first, A and B as one of the inputs, and then OR B is the other input over here. And then over here, the last part of this one is write a Boolean expression for the following situations. The right turn signal of a car is turned on when the right turn signal is activated, or the hazard flasher is activated. And the left hand has to be turned on when the left turn signal is activated or the hazard's activated. How do you do this one? This one's a little bit more complex. It's got to be, if you read it carefully, you'll see that one, or the hazard's activated. And this one's turned on when the left turn signal is activated or the hazard's activated. And so you can actually do a 3-input one. So here's the right-hand turn signal. That's supposed to be an input over here, just a dot. You got the hazard over here. I'm going to label that as an H. And I'll put the left down here. And I'm actually going to draw this as a circuit, not as a Boolean expression, just because it makes it easier. And I'm just going to use some OR gates. One OR gate here and one OR gate here. And over here is the right tail light or turn signal. Or sorry, what did I call it? Yeah, I'll call it the right tail light. And so that should go on if the right-hand turn signal is turned on or the hazard is turned on. And over here, the left-hand turn signal, or the left-hand, tail light, should turn on if you turn on the left turn signal, or again, if the hazard's turned on. And so you can quickly figure out all the rest of these. I didn't do an example from part 1, but I think you should be able to sort of figure this one out. Good luck with your homework tonight. Your homework is finishing off the worksheet. Again, hopefully you've cleaned up all of the robotics parts without any problem. And I will see you next week. Good luck, everybody.